one term in physics and chemistry that's very difficult to define is an idea called entropy. We're going to define entropy both on a macroscopic level, or a grand scale, and on a microscopic level, very small atomic scale. First, we'll talk about the macroscopic scale, in which entropy is related to the amount of energy that's unavailable for work. So let's look back to those thermodynamic processes, like for a cyclic process, a machine. And so a machine has a certain amount of energy put into it from heat. Some of that heat goes into doing work, but some of the energy must be removed to get us back to original conditions. So not all of the energy can go into doing work. And therefore, some of the energy is unavailable for work. And that's what entropy is trying to describe, the amount of energy that cannot go into doing work. Now, on a microscopic level, we're talking about the motions of the particles, and the more entropy there is, the more randomness there is to the particles. Some people talk about the disorderedness of the particles. Now, they use an analogy sometimes, like our filing cabinet, that if I file things away, there's less disorder and therefore less entropy, and as things get cluttered, there's more disorder and more entropy. We have to understand that these are analogies. It's not really saying that this clutter of paper, we could actually calculate its entropy. That's not what we're referring to here. So I talk more so about the randomness of the particles, and that entropy is really a measure of the number of ways that a system can be arranged. Now, the colder a substance is, the less entropy it has. And the hotter a substance is, the more entropy it has. And here's a reason why. In a solid, something that is cold, the particles are more tightly bound to each other. And so therefore, there's less ways that they can be arranged. They have to be arranged in some crystalline structure. So they have to be arranged in a certain way. So there's less ways that we can arrange that system and less randomness. They're more organized. As we heat it up, we turn it into a liquid, the bonds loosen up, and we turn into a gas, and the bonds break apart. And so now the particles are just moving haphazardly around. And so there are more ways that the particles could be arranged. There's more patterns as to how the particles might look. And so there's less organization, and therefore more ways that the system can be arranged, the particles can be arranged, and therefore more entropy. So as we heat things up, things become more random, and therefore there's an increase in amount of entropy. Now, the second law of thermodynamics says that the total entropy of a closed system, and that's important here, a closed system will either stay the same or increase. It will never decrease. Now, that's not to say we can't decrease the entropy of an object. Let's say that we have a cup of water, and we put an ice cube in that water. And so what happens is the temperature of the water goes down. And what we had said before, according to entropy, is the randomness of the particles. As the water decreases in temperature, its entropy goes down. Now, that's not a violation of the second law. What happens is, though, that the ice cube warms up, and so the entropy of the ice increases. Now, the entropy of the ice is, the increase in the entropy of the ice must either be the same or greater than the decrease in entropy of the water, so that the total entropy of our system will either stay the same or increase. So when we're talking about a closed system, we're saying there's nothing outside our system. There's no heat transfer with anything outside that object. And so when we talk about in this case, a closed system, something can decrease in entropy, but something else must increase by the same or more, so that the total entropy either stays the same or increases. Now, applying this second law of thermodynamics back to our idea of entropy is related to the amount of energy unavailable for work, we get that eventually we'll come to something called the heat death of the universe. Eventually, all energy that's available for work will become unavailable for work. As the entropy continues to increase and continues to increase, more and more energy becomes unavailable for work, and eventually no work can be done. At this point, all thermodynamic processes stop, and everything reaches thermal equilibrium. So everything's moving, all the particles are moving at the same speed. And therefore, there are no machines that can exist that work off of a single temperature. Remember, we must always have a cooling system for a machine to work. And so if everything reaches the same temperature, that means that no machines can exist, the human body cannot function, all life no longer exists, and therefore all thermodynamic processes will cease. So again, entropy, the amount of energy unavailable for work. We can also refer to it as the randomness. The hotter a substance is, the more entropy it has. And the total entropy of a closed system either stays the same or increases. At some point, now this is trillions of years down the line, all energy available for work will become unavailable. Everything reaches the same temperature, and therefore all thermodynamic processes stop.